Cool. Cool. Sweet. So, hello and welcome to this Math2801 / Math2901 revision workshop. This is going to be divided into two parts. So, today from 12 to 2, me, Noah Rubin, and Jerry will be covering this section of the course, and then tomorrow, Jerry and Bruce are going to be covering the second section of the course. So, I guess the whole point of this workshop is to try just cover all the terms content in like a, clear and concise manner. And, this workshop, while it's being streamed live now, we'll also release it like publicly. We'll like list it and everything, so you can watch it like another time as well. We've got some practice questions as well as like theory, so it's just aiming to be a nice like little compact way of summarizing what stats is all about, at least in this context. So I'm going to be covering topics 1, 2, and 3, and sort of 3.5 as you'll see later. And then Jerry's going to cover 4, 5, and 6. And together that will make up part 1. If you're wondering where things like, maximum likelihood estimation are and things like that, that will be in the second section. So nothing to worry about there. Sweet, let's get right to it. So the first thing that you would have covered in the lectures is sort of just like an introduction as to, what probability is and some basic definitions. So here are some definitions that we won't go into too much in depth. And especially because I believe Libo, the 2901 lecturer, mentioned that sigma algebras won't actually be in the exam, and 2801 don't cover it. So here are some basic definitions that you can sort of refer to in case they ask them. So, if they ask what a sample space is, here it is, and things like that. Pretty standard, but we know that probabilities must lie between 0 and 1, so we can't have negative probabilities, and we can't have something like have like a 102% chance of happening. Probabilities must all like sum up to 1, so if the probability of a head is 50%, then the probability of a tail will also be 50%. And for any two events, we have this rule over here. So the probability of A union B is the probability of A plus the probability of B minus the intersection. So the idea here is that if we have two sets A and B, we consider all of A. So we've shaded in this middle part once. We consider B, so now we've shaded in this middle part twice. So we need to strip off the middle part once. So we count all of A, count all of B, and then we strip off the middle part once because we've double counted it. Now, in the case where we have what we call mutually exclusive events, there's not going to be any intersection, so the third term there will be equal to 0. And that will be pretty important when we actually consider some practice questions. Again, if you are, if you want to get like a little bit more in depth as to like formal definitions of like probability spaces, we have this thing called omega, this weird looking character here, which is your sigma algebra, and like this probability function here. Let's not go too in depth with this, especially since it's not going to be in the exam. But here's like an example of what omega, your sigma algebra, and p represent in the case of like a coin flip. So omega being like all your possibilities. This is just representing the fact that we could get like nothing, a head, a tail, a head and a head, a head and a tail, and so on. And probability maps between 0 and 1. We have this thing called conditional probability as well, where this vertical bar means given. So the way I guess you would read this is the probability of A given B is the probability of A intersect B over the probability of B. And what you'll see here is that if the probability of B is 0, you're going to run into serious problems. So we do require that the probability of B is greater than 0. Okay. Now you'll see that we get this identity here, the probability of A intersect B, as this, and the way in which we got that is simply just timesing both sides by probability of B. So if you take this expression and multiply both sides by the denominator, you get nothing but that. We can, of course, generalize this to 3 events. Here's the formula for when there is a, intersect C component as well. And I guess in the case of the exam, You just have to you'd have to identify what your A and your B and your C events are, and then you just whack it into that formula. Cool. We also have this thing called independence. So two events are independent if and only if we can represent the probability of the intersection as just the individual probabilities banged together. And what we're saying there essentially is that the probability of A given B is just the probability of A. So the fact that like B happened has no real effect. Cool. And that's sort of what's happening here. And you can apply the same for B too. So here's a question that sort of combines this all together. So what we have to do is let A and B be two events in some sample space with positive probability. So just notice there the probability of A is greater than 0 and the probability of B is greater than 0 as well. So what we have to show is that if A and B are independent, they cannot be mutually exclusive. Cool. So for this one here, actually let me I think I'll do the solution from scratch. So just by definitions, what we have is that the probability of A intersect B, just from definitions, is equal to the probability of A times the probability of B if independent. So if independent, we could just sort of bang the two probabilities like that together, right? And that's if A and B are independent. So if A and B are independent. Right, so that will apply. Now the problem here is that this part is greater than 0 and this part is greater than 0 as per the question. So they cannot be mutually exclusive, because if they are mutually exclusive, then the left-hand side is going to be 0 and the right-hand side is going to be something greater than 0, right? So what we have is with mutually exclusive, there's no intersection, so the A intersect B is the empty set, which then implies that the probability of A intersect B is 0. There's like a 0% chance of it happening. And so what we're gonna have here is we're gonna have like 0 greater than is equal to something greater than 0, which of course is false. Because this right hand side is greater than 0 and this left hand side is 0, it can never happen. So if A and B are independent, they can't be mutually exclusive. And that's sort of what you're seeing. That's what you're seeing there. Okay. Now we have to show that if A and B are mutually exclusive, they cannot be independent. So if they are mutually exclusive, what we have is we have no intersection. So the probability of A intersect B is equal to 0, right? It can't happen. And this, of course, they can't be independent, because if there was independence, we'd have to have it equaling the probability of A times the probability of B. But that can't happen because, again, this is greater than 0 and this is greater than 0. So that can't happen. So if A and B are mutually exclusive, they can't be independent, since we were told in the question that the A and B's had positive probabilities. Cool. This is probably the least intuitive, so I'll probably go most in detail into this one. So the way in which this works is, now suppose that A and B are mutually exclusive, show that that identity is true. And so I know it looks hard, but it turns out that all you need to do is just remember what conditional probability was. So we know that the probability of A given B is the probability of A intersect B over the probability of B. That's just from definitions a few slides ago. Now what you'll notice here is that our B is really A union B. So wherever we see B in this formula, we're just gonna sort of almost sub in A union B, like that. And so what we get in our case is as follows. So the left-hand side is the probability of A given A union B. And that's going to be equal to, well, wherever we see B, we just sub in A union B. So the probability of A intersect, now B is A union B, over the probability of B, but B is really A union B, like that. Now we can use a little bit of set theory. So what we can say is that this is A intersect A union A intersect B. You can almost like expand it. So what we get here is the probability of A intersect A union A intersect B. Like that. Over the probability of A union B. Cool. Now what you're going to see here is that what we get, I'll just move it over here. So what we get is the probability of A intersect A is just A. And A union, now this is actually going to be the empty set because they're mutually exclusive. Right? They're mutually exclusive. So that's going to be the empty set. So this is actually just going to be the probability of A on the top. So A union empty, which is just A, over the probability of A union B. And this is equal to the probability of A. Now the probability of A union B, just from earlier slides, is you sum up the individual probabilities and then we minus the intersection to avoid double counting it. So probability of A intersect B. Now because of the mutually exclusive condition, there is this probability that A intersect B is just 0, right? So we can almost just sort of, kind of while no one's looking, just cross it out. And that's because of mutually exclusive events. The fact that A and B are mutually exclusive. So that part's just 0. And what you see is that the left-hand side now is, we fiddled with the left-hand side to generate what we wanted on the right. Cool. Lovely. We now have independence for multiple events. So for 2 events, you could just, if AI is an event and AJ is another event, we know if they're pairwise independent, you can just bang on their individual probabilities together. Event I can't be the same as event J, so your I and J subscripts have to be different. Now we can actually generalize this to more than, we can generalize this to like a wider set of events. So all we're really seeing here is that the probability of the intersection of a whole lot of different events is just multiplying each individual one together. So we take the product from J equals 1 to M. So if you look at this is going to be the probability of AI1 times the probability of AI2. Probability of AI1 times probability of AI2 times probability of AI3, and so on. And what you can see is that if you sum from J equals 1 to 2, that is like pairwise. But the fact that we can sum from J equals 1 to M means that we call it like stronger than pairwise independence. Okay. Here's a law of total probability. You can use this to find a quantity PB, but really all this is used for, at least in this context, is for Bayes' theorem. So you would have seen Bayes' theorem in like Math2801, and when you're calculating the denominator in Bayes' theorem, you get this. I mean, it's worth like doing a few examples, and you'll see that you do generate this in some sort of way. And I guess what you can do is, with 1 or 2 examples, just see like exactly what your AIs are that you're like summing across in the denominator. But there's like a formal definition. But you have been using it like this whole time when you've been doing Bayes' rule. Cool. So we move on to this concept called random variables. So a random variable, basically here it is, right? They can be thought of as variables whose values depend on the outcomes of a random experiment. So, if we're flipping a coin and we want to like count like the number of heads, or something like that, that in itself is like a random experiment. And so, we can call that like a random variable. So like the number of like heads you land on or something like that. Or in the continuous case, we could look at like the heights of like kangaroos or something. Who knows? And we typically denote these with capital letters. So that's going to be capital X, to distinguish them from like non-random variables. So anytime you see like a capital, that at least in statistics, you can think of it as a random variable, at least most of the time. Cool. And we'll get into plenty of examples of this as well. It turns out that random variables, when talking about random variables, it sort of leads naturally onto the concept of cumulative distribution functions. So we call this cumulative distribution function a CDF for short. And basically, we define it as this. So if we have a point x, I don't know, if we have a point x, let's just say this is a distribution. All that we really do is we just sort of sweep up all available probability up until that point x, like that. So if we wanted to find fx3, we just, sweep up all probability up until the point 3. And so what we do is we define it as the cumulative distribution function for our random variable, capital X, like that. Now, because probability must all sum up to 1, you can take the probability that our random variable is greater than a particular point by just doing 1 minus. You could find this guy by doing, you can find this guy over here by doing 1 minus all of this. So, I mean, just in short, you can probability must sum up to 1, so this identity has to be true. Now, if we want to find the if we have just a random distribution here, and we want to find the probability that x lies between lowercase x and lowercase y, all that we have to do there is just take all the area up until y minus all the area up until like that area minus the second area that I drew, and what you then get is, of course, that bit there. Okay. Yep. So now with cumulative distribution functions, it's only ever going to be increasing, right? Because as you sort of like sweep up more probability, it will only go up. So let's just say we have a cumulative distribution function that looks a little bit like that. Now we know that as we sum up all probability, it'll never be above 1, so its limit as x approaches to infinity will be 1, and its limit as x approaches negative infinity will be 0, because probability can never go below 0, right? So you start at 0 and you just accumulate more probability, and that's why it's always ever going to be, it'll never be decreasing, your function, it'll never ever be decreasing. So f is non-decreasing. Now, it's also right continuous, so this limit definition holds true. So as you approach it from the right, it's you don't get any like sort of weird behavior. It is right continuous. Cool. We have this concept called discrete random variables. You'll see what continuous random variables are soon, but a discrete random variable takes on a countable number of values. And so what we have is our probability mass function, which we call lowercase f of x, so the probability mass function for our random variable x. Basically, all that we have is, in the discrete case, we would have like a whole lot of bars, and the mass at a particular value is just like the height of the bar, right? So if we want to find like the probability that x is equal to like 4 or something, we just take like the height of that bar, and that will give you the probability. And then again, if we want to find the cumulative distribution function, you just sort of take, you sweep up all probability up until a particular point. Okay. We also have continuous random variables, so they can take on a continuum of values, contrary to a discrete random variable that can only take on like a very like countable number of values, whereas continuous can take on, a continuum of values, in the sense that like heights, for example, would be a continuous random variable because you can be 169.32159 centimeters tall, and you can just measure it to like an arbitrary amount of precision. So with a continuous random variable, we can find the probability that our random variable lies between 2 points A and B by just computing an integral, and the cumulative distribution function for our random variable x can, again, you basically just accumulate or sweep up all available probability up until a point x. Okay. Cool. So we have this thing called symmetric random variables, which they've sort of introduced in this question, and we'll see how it all sort of plays out. but let's just have a look at what this is. So a continuous random variable x is said to be symmetric if x and minus x have the same CDF. On the other hand, a density function f is symmetric if f of x is f of minus x for all real x. So show that this quantity here is the same as this quantity here. Okay, so from definitions, we know that fx, x, if you just look back onto this slide here, you'll notice that, oh, maybe it's a bit far. Yeah, here it is. So that's just the probability that x is less than or equal to a particular value, lowercase x. Right? So you just use that definition. Now, what we can see from this is that 1 minus f of x is equal to 1 minus whatever that is, right? Which we've determined to be that. Okay? And so what we can say is, this of course is the probability that x is greater than x. And that was from a few slides back as well. Okay? So how can we use this in our case? Well, what you might notice is that we want minus x, so the only thing that we have to do is patch up a minus x there, but then of course patch up a minus x there. And so that's exactly what we're going to do. So what we're going to say is that f minus x, x, and if I change it there, I'm going to have to also change it over here. So minus x is less than or equal to x, like that. Now we can simply just rearrange this. So we can rearrange this, and what you're going to see now is that we're going to get the probability that x is greater than minus x. So I mean, you could just move that to the one side. So you can move that to that side and move the x to the other side. And what you're going to see here is that this is looking very similar to this. And so what's changed here, we've just slipped in a minus x there and a minus x there. And what you're going to see here is that this is equal to, well, exactly what we wanted, right? So 1 minus the cumulative distribution function for our random variable x, and minus x. So that's the first part, just straight definitions, nothing really too complicated there. Hence or otherwise, deduce that a random variable x is symmetric if and only if the density of x given by the f for our random variable x is symmetric. Oh, what a mouthful. So what we know is f is symmetric. So I mean x is symmetric. So our random variable is symmetric if we can write, they said if the cumulative distribution functions were the same. So what we want is the cumulative distribution function for our random variable x is the same as the cumulative distribution function for our random variable negative x, i.e. they have the same CDF. So what we know is that from the first part, so from I, what we know is that, I mean, you can see this for yourself, but just, here it is. So 1 minus f x minus x. Like that. Cool. Okay. Now, what we can do is we can take a derivative of both sides. So what we can say here is that we can take a... Oh, and the reason why I got this, of course, is because... well, I mean, yeah, you can just check part 1. So this is just from part 1. Now, what we can do is we can hammer a derivative on both sides. So what we can say is just d on dx both sides. And what you'll see there is that what we get is, on the left-hand side, the derivative of a CDF is in fact your probability density function. So what we're going to get here is just the probability density function for our random variable x. And on this side, what do we get? So we get the derivative of 1 is 0 minus fx minus x, and then by the chain rule, we have to also times by the derivative of the inside. So we're going to have to times by -1. And so what we get here is that fx x is equal to, negatives cancel, so we get fx minus x. Cool. And so what we see that x is symmetric. Now, the converse also applies, because you could integrate both sides. you can integrate both sides here, and you get back to just as if there was no d on dx operator there. Now you'll be out by a plus c, but that plus c will always be 0 because if it's not 0, we risk pushing our cumulative density function outside of like the interval 0, 1. And so what you're going to see here is that it can all be summarized just from that. Cool. So if you integrate both sides, so if you start at the star and you integrate both sides, what you get is this top line. You'll be out by a plus c, but that plus c has to be 0 in order for these definitions to be valid. Okay. Cool. So we have this concept called expectations in statistics, which turned out to be very, very important. But the expectation operator is valid for both continuous and discrete random variables. So for discrete random variables, we just take all possible x and we times a particular x value by the probability of your random variable equaling that particular x value. And we do that for all possible x. Now, in the continuous case, the summation just turns into integral, and you're doing the same thing. So you take x and you times it by your PDF function. Cool. Now this e of x can sometimes be denoted as mu or mu sub x. It's all, synonymous. Cool. Now the only change that happens if I move to an arbitrary function g of x, so we had just x over here. If I move to an arbitrary function g of x, nothing really changes apart from the fact that instead of x, we just have g of x. And this summation for discrete and the integral for continuous still remains the same. The expectation of a constant is just that particular constant, and what we can do is realize that expectations are linear. So you could almost like expand this, and you get this quantity here. So you can take constants a and b out of the summation, and you can also distribute the expectation throughout both terms. Now, unfortunately, this part isn't always true, but it is true in the case where x and y are independent random variables. So the expectation of the product is the product of the expectations if your x and y variables are independent. Cool. We also have this quantity called variance, which in applied statistics is like the it's a measure of spread to see like the how your observations deviate from the mean. But the way in which we can denote the variance of x is this line over here, but very conveniently we can actually write it in terms of expectation, which makes things very nice and easy. Okay, so whenever we see the variance of x, more times than not, we want to actually write it in terms of this form because it makes it a lot easier. We can sometimes denote the variance as sigma squared, and the standard deviation, we can just square root the variance, because standard deviation is just the square root of the variance. So if the variance is sigma squared, then the standard deviation has to be sigma. Cool. If we take the variance of a constant times a random variable, you can take the constant out. The only condition is you do have to square it. If you take the variance of a constant, that's 0 because there's no spread. And we can write the variance of x as the covariance between x and itself. And Jerry will get more in depth about what covariance is, but just, yeah, for now, recognize that this identity very much is, it's very much true, and you can just use it. If we shift a constant, it's as if we just like rubbed out the constant. So basically the variance of x plus a constant a is just the variance of x. And unfortunately, variance isn't linear, so you can't just say that the variance of x and y of x plus y is the variance of x plus the variance of y. You are out by a middle term here, which captures the covariance. But it turns out that if x and y are independent, you can actually delete this covariance term, and you do get like the variance of x plus the variance of y. So it does have that quality if x and y are independent, but if x and y aren't independent, you have to consider this middle covariance term. Cool. So we have this proof here that we have to use the definitions of expectation and variance for, and what we want to show is that this m of theta hat function is the same as this b of theta hat function plus the variance of theta hat. And theta hat is a random variable, So we can use all the laws that apply to random variables there, and theta without the hat is a constant. So what we're going to do is we just do like a simple left-hand side equals right-hand side sort of thing. So the left-hand side is equal to m of theta hat. And we've been told what m of theta hat is. So m of theta hat is nothing but this term over here, which I'm actually going to expand now. So what we get is e of, and if we expand what's on the inside, we get theta hat squared minus 2 theta hat plus theta squared. So, a squared minus 2ab plus b squared. Lovely. So what we get is, remember, expectation is linear, so we're going to run expectation through each of these terms. So we get e of theta hat squared minus e of 2 theta hat plus e of theta hat. Just theta squared, sorry, not theta hat. So just running expectation through each of those terms there. Now what you're going to see now is that theta hat's a random variable, and squaring it, it's still random, so we can't really do anything with that. So we have to just, leave it the way it is. Now, theta is a constant. So theta without the hat is a constant. So 2 theta is also a constant. So we can take that out. E of theta hat. And then the expectation of a constant, because remember, theta is a constant, so theta squared is also a constant. The expectation of a constant is just a constant. So we can just pretend the expectation was never there. Okay? Yeah. Now, we're going to have to deconstruct the right-hand side. So let's have a look at the right-hand side. And I'm going to break it up into this b of theta hat squared plus variance of theta hat. So let's just take a look at what b of theta hat squared is. Now, we know that b of theta hat without the squared is just this, e of theta hat minus theta hat, or theta. And what we can do is just by squaring it, we can just square that as well. Okay, so what we get here is nothing but e of theta hat all squared. So we can say e of theta hat all squared minus, so a squared minus 2ab plus b squared. So minus 2 theta e of theta hat plus theta squared. Okay, cool. Now we can take a look at the variance. So the variance of theta hat, just remember from a few slides ago, we typically prefer to write it in terms of expectations. So the variance of x is the mean of the square minus the square of the mean. So what we can say there is that is going to be equal to e of our random variable squared minus e of our random variable all squared. Okay. And so what we can argue now is that the right-hand side here, so the right-hand side, which is equal to the, b of theta hat squared plus variance of theta hat, we can just write that. So that's going to be nothing but this line over here. So e of theta hat all squared minus 2 theta e of theta hat plus theta hat, or theta squared, just rewriting that line over here. And then what we have to do is you have to plus the variance. So plus e of theta hat squared minus e of theta hat all squared, like that. And what you're going to see here is that this, so this part is nothing but b of theta hat squared, and this is variance of theta hat. So what we notice here is that the square of the expectations cancel out, and so what we get is the left-hand side. So I'm just going to write it as this guy over here, so that's going to be e of theta hat squared minus 2 theta e of theta hat plus theta squared, which you'll actually, if you look up, you'll see that, it all sort of matches. So that's equal to the left-hand side. So, yeah, I mean, basically all that we had to do there is note that you can take constants out of the expectation. Expectation's linear, and variance can be written as the mean of the square minus the square of the mean. Cool. Yeah, hopefully no, I don't think I've made any mistakes there. Okay. We can use expectation and variance in a slightly more applied setting, with like summations and integrals rather. So here's another question in which you will need to use that. So what we have to do here is suppose that x is a continuous random variable with probability density function f of x. So the probability density function for your random variable x is given as this. And what we have to do is we have to find a k such that this probability density function is valid, right? And what I mean by that is that if we sum all the probabilities up together, it has to equal to 1. We can't like sum up all probabilities and have it like not equal to 1, because then it's not a probability density function. Cool. So what we're going to have to do here is we're going to have to just note that, generally speaking, if we take the integral over our entire, values that it can take on. So if you take the integral over its entire support of a probability density function, what we need is that we need this to be equal to 1. So as I collect all probability from negative infinity to infinity, I have to get 1. The area under the curve has to be 1. Okay. Now in our case, our f of x is defined like this. So what we can say is that the integral, what we need is the integral. We don't actually have to go from negative infinity to infinity because our function's only defined between -1 and 0. And so what we can say is that we can say that, over -1 to 0, we have to have all probabilities sum up to 1. So we can say, k times x squared plus 2x plus 1 is equal to 1. Cool. We can take the k out. So we can take the k out, and that's going to be -1, 0 of x squared plus 2x plus 1 is equal to 1. And, just to keep things formal, I'll put a dx there because we're integrating with respect to x, not with respect to k. Dx. Cool. Now what you're going to notice here is that you get, just by doing a simple 2-unit integral, like a year 11 integral, year 12 integral, you can basically, just add 1 to the power and divide by the power. So what we get is that plus x squared plus x between -1 and 0. And we have to set that equal to 1. Cool. And so what we get is if you sub in the top minus sub in the bottom, you're going to get k on 3 is equal to 1. And so, k has to be 3 in order for that to work. Okay. Cool. So what you'll see there is that if you integrate this function considering k equals 3, you'll see that the integral over its entire support is 1, right? As we needed it to be. So now what we have to do is you have to compute the expectation of x. Now what you'll notice is that the expectation of x was defined in terms of an integral earlier, and that's exactly what we're going to do now. So what we want to do now is calculate the expectation of x. So generally speaking, the expectation of x is equal to the integral over your entire support of x f of x dx. Now, in our case, our bounds will be a little bit different, so we just have to account for that. And what we're going to get here is that the expectation of x is equal to the integral over our entire support, which is just that for us. And what we get here is x times your density function. So our density function was k, which we know is 3 now, times x squared plus 2x plus 1, like that, dx, of course. Now, there is nothing trying to trick you here in this integral. You can just integrate this however you like, but just expand the terms, and what you'll see is that you get nothing but -1/4. So, you could chuck this into Symbolab or eMath Help or something like that can compute integrals, and what you're going to get is -1/4. So we'll assume that, you guys are comfortable with integrating, just for time purposes, I guess. Cool. So that's the expectation. Now the variance can always be written in terms of expectation. So what we can say is that we know that the variance of x is equal to, the mean of the square minus the square of the mean. And so all that we want to do is we have this guy already, right? So all that we really have to do is find that. So what we can say is that the expectation of x squared is equal to the integral over our entire support, and instead of x f of x dx, we're going to do x squared f of x dx, like that. Now in our case, the thing here is just x squared times our density, so 3 times x squared plus 2x plus 1 dx. Cool. And what you're going to see here is that if you do compute this integral, it's quite a laborious calculation, not particularly hard, but just, takes a while. And what we're going to see here is that you get 1/10. Okay? And because of this, we have everything that we need. So the variance of x is nothing but the expectation of x squared minus the expectation of x all squared, like that. And you'll see that we get 3/80. Cool. And that's all you need. So I did skip the integration step, but that's nothing but, what you've seen in a HSC or... Okay. Cool. So we now move on to this concept called moment-generating functions. So moment-generating functions are quite useful. I mean, here are the reasons why they're useful, and then we'll see how we can calculate them later. But basically, we have this thing called a moment-generating function, where we have the moment-generating function for our random variable x is nothing but the expectation of e to the power of tx. Okay? And this lowercase m could have been written as capital M, so I could have said, the moment-generating function x of t. I could have said that. Some people also call it, phi x of t. You might see that around somewhere, but, it's all synonymous. And the way in which we find it is by taking the expectation of whatever e to the power of tx is. Cool. So moment-generating functions, what we can find with moment-generating functions is the non-central moments of a distribution. So, for example, for a Poisson distribution, which Jerry's going to cover soon, we can find the first or second moment for that. Or, for a normal distribution, we can find the first and second moments of that as well. And higher order moments on top of that. Another way in which we can use moment-generating functions... Another way in which we can use moment-generating functions is to identify distributions. So each distribution has its own sort of moment-generating function, and observing that moment-generating function, you can then say, okay, this is going to be a gamma distribution or a Poisson or binomial or whatever. So each moment-generating functions are unique to a distribution. They belong to that particular distribution. So as I said, we can compute first moments, first non-central moments, second non-central moments, third non-central moments for any sort of arbitrary r. And that's the beauty of moment-generating functions. They generate moments for us, so we can find the first moment, second, and so on. The way in which we actually compute this is by taking the limit as t approaches to 0 of this thing over here. So basically, in summary, once we have our moment-generating function, if we want to find the rth moment, all that we have to do is find the rth derivative and then sub in t equals 0. Not all the time are you going to be able to sub in t equals 0. There will be cases, maybe sometimes, where there'll be a little bit of misbehavior at t equals 0. So we can overcome this in the notation by just observing that we can take its limit, and that's like a little bit more robust. So we can find the rth moment of our random variable x by taking the limit as t approaches to 0 of the rth derivative of our moment generating function. That's sort of how you interpret that. Cool. So that's that. Let's actually apply this to a particular question, and we'll see where all this theory comes into play. Cool. So let x be a random variable with probability density function defined as this. Find the moment generating function of our random variable x. Okay. Cool. So what we do is we just observe definitions again. So we know that the moment generating function for our random variable x is nothing but the expectation of e to the tx. So what we can do is we can say e to the tx like that. Cool. And what we know now is that we can write this as the integral over our entire support. So our support is x can go from a to b. So we write our bounds as a to b. Right? And then by definition of expectation, you take whatever's inside here times by your density function. So what we're going to say is whatever's inside there times your density function. So times 1 over b minus a. Like that. Dx. Okay. You'll notice that this b minus a has nothing to do with x. We're integrating with respect to x. And these b minus a's are just constants, so we can take it out of the integral. And what we're going to get here is the integral from a to b of e to the power of tx dx. Okay. Now again, nothing overly complicated about this integral. All that you do is, e to the f of x over f dash of x, and yikes, my bad. So we're gonna write like e to the tx over the derivative of tx, which is just t, and we're going to evaluate that between a and b. Right? Okay. And so what we get here is 1 over b minus a. And what we need to do here is, sub in top minus sub in bottom. So what we get is sub in the top, and we get e to the tb minus e to the ta. That one's going to be over t, and that one's going to be over t. So e to the tb over t minus e to the ta over t, and we get that quantity there. We can put it all over one denominator, so we can say 1 over b minus a times e to the tb minus e to the ta over t. And we can just, write this without any messy brackets, so we can say e to the tb minus e to the ta over b minus a times by t. Like that. Cool. You might immediately wonder, well, okay, I mean, here's the process that we went through. So we take the, we take the expectation of e to the tx, and we do the integral, and we find our answer. And now we sub in t values for our moment generating function. So you might be wondering, what happens if t is 0? And as you can probably see, when t is 0, we run into problems. So when t is 0, we get a 0 denominator, and 0 denominators are, of course, problematic. So we have to observe, to actually find the moment generating function in its entirety, we have to look into what actually happens to our moment generating function when t is equal to 0. So basically what I'm just going to say here is considering the case where t is equal to 0. Let's just see, for completeness, what actually happens to our moment generating function when t is equal to 0. So what we get is, subbing in t equals 0 will be problematic. So let's take its limit. So the limit as t approaches to 0 of our moment generating function e to the tb minus e to the ta over b minus a times t. Like that. If you actually, I mean, it's worth having a crack. It's worth having a crack and subbing in t equals 0, because you might actually, you might actually get lucky, but in this case you don't. In this case you get e to the 0 minus e to the 0 over b minus a times 0, and this is 0 over 0, so we get like an indeterminate form. So we can't actually take this limit. So to see what happens when t is equal to 0, finding this limit's sort of redundant because we get an indeterminate form. So what we actually need to do is, if you remember from first year math, we actually have to appeal to L'Hopital's rule to actually work out what this limit is. So what we can actually do is, instead of taking the limit as t approaches to 0 for this function, we can see the limit as t approaches to 0 for the derivative of the top and the bottom, and you'll see what that means soon. So using L'Hopital's rule. Okay, so if we use L'Hopital's rule, what we get is the limit as t approaches to 0, and what L'Hopital's rule says is we can differentiate the top fraction symbol, differentiate the bottom, and take the limit of that. So let's differentiate the top. That's going to be be to the bt, or tb, minus ae to the ta, right? And we can, differentiate the bottom, so the derivative with respect to t on the bottom is b minus a. And just keep in mind there, I wasn't using quotient rule. This is not the same. All we're doing is we're differentiating the top line, differentiating the bottom line, and then taking that limit as per L'Hopital's rule. So what we can do here is now we can have a crack at subbing in t equals 0. So what we get here is b times e to the 0 minus a times e to the 0 over b minus a. And what we get is, b minus a over b minus a, which is, of course, 1. It's equal to 1. Cool. So what have we actually said here? Well, we've sort of noticed that our moment generating function is defined differently depending on t. So our moment generating function in terms of t has two possibilities. So there's going to be a case where t is not 0, and there's going to be a case where t is equal to 0. If t is equal to 0, we just found that our moment generating function is 1, right? Just, observing the limit and things like that. And if t is not equal to 0, we have no problems with that denominator. Assuming that a is not equal to b, right? We have like a clear difference between what a and b is. Assuming t is not 0, we get a nice function over here. So we get e to the tb minus e to the ta over b minus a times t. Like that. Cool. So that's how it works. So here's your moment generating function in terms of t of this quantity over this quantity here. And that's it. If you wanted to find the first moment, i.e. ex to the power of 1, you just take the derivative of this function with respect to t. It's quite a complicated one that you would have to use probably quotient rule for. You take that derivative once and you set t equal to 0, or you take its limit as t approaches to 0. If you want the second moment, so the second non-central moment, i.e. the expectation of x squared, we would take the second derivative and take the limit as t approaches to 0. And that generalizes to higher values of r. Cool. Yep. So that's that. So that's going to be my section done. Jerry's going to take over for the rest of it, and he's going to cover everything from parts 4 to 6. So if you notice here, everything from here onwards. Cool. And I'll pass it on to him now. Oh, wait. Yeah.
value A, the probability that the random variable is greater or equal to A is going to be less than or equal to the expectation of the random variable over A. And the second one is Chebyshev's inequality, where if X is a random variable with mean, U, and variance, then for any K, we have this formula. And what this formula kind of shows is that for K, we get that the probability that X, a value X of the random variable, is greater than K standard deviations is less than or equal to 1 over K squared. So let's start with a question. A factory produces 500 machines a day on average. It is subject to a variance of 100. So first off, we have that mu, or the average, is 500, and the variance is 100. Let X be the amount of machines produced tomorrow. Find a lower bound for the probability that between 400 to 600 machines are produced tomorrow. So we want to find the probability that X is going to be between 400 and 600. So this is what we want to find. And we'll find that this value is also equal to this value, because that's just kind of the absolute value. Because if we have from 500 over here, this absolute value interval just means that we go between 400 and 600, we go 100 out. And because we can't calculate this straight away, because if we look at Chebyshev's inequality, we see a greater than or equal to symbol, and we have it in terms of a less than symbol. So what we're going to do is find 1 minus of this value to get this greater than or equal to symbol. And then now we know that this value, using the formula, is going to be less than or equal to 1 on K squared. And here we can see that here the mean is 500, and 100 is just 1 times the variance, because this is 1 times 100. So since K is equal to 10, by Chebyshev's inequality, this probability is going to be less than or equal to 1 on 10 squared, since K equals 10. And if we return back to the value that we want, we know it's 1 minus the value of 1 on 10 squared. So the lower bound is 99 over 100. We also have Jensen's inequality. So a function h is convex if for any lambda between 0 and 1. So I'll just draw a convex function. So a convex function is where if you pick 2 points of the function and you draw a line, the line is going to be above the function. So what is written here just kind of expresses what I've drawn. And what Jensen's inequality says that if x is a random variable and h is a convex function, so h kind of looks like this curve here, then we'll have that h of the expectation is going to be less than or equal to the expectation of hx. We also have that if the function is concave, which is the opposite of convex, so if we pick 2 points, the line we get is going to be below the function. So when this is the case, this result is just going to be reversed. Okay, so I've finished this chapter, so I'm going to move on to common distributions. So for this chapter, I'm mainly just going to be going over what the common distributions are and not doing too many questions because the later chapters kind of just build on the content on this in this chapter. So there's a formula sheet that contains details of the important distributions. And yeah, later down, I have the formula sheet in the presentation, so I'll just show you how to use it. And a lot of the probabilities associated with these distributions can easily be computed using R. However, for some distributions, the parameters are defined differently. So Bernoulli distribution is where there are random models, whether a trial will be a success or a failure. So a Bernoulli variable is going to model whether there's a success or a failure. And a binomial distribution is when you have n Bernoulli trials with success P. So the geometric random variable models the number of trials it takes until the first success occurs. And the negative binomial is a generalization of the geometric distribution. When it comes to the hypergeometric distribution, we don't have to worry about it. So I'll just skip over it for now. A Poisson random variable models the number of occurrences of a random event that occurs at a rate of lambda on average. Unlike binomial random variables, Poisson random variables are not bounded above. So when I say that it models the number of occurrences of a random event, so an example might be within a given time period, how often does a computer crash? So the model would be modeling the number of crashes per time interval that we select. A uniform random variable has a constant density function. It is equally likely to take values in any equally sized region within AB. So this one's quite simple to draw. So for the density function of this distribution, if we have A and B, the density function is just going to be constant, and the area underneath is obviously going to add up to 1. An exponential random variable is often used to model the time it takes for an event to occur. So as opposed to the Poisson distribution, which is how many occurrences occur in each time interval, an exponential variable models the time it takes for something to occur. So it could be the time you take to wait for a bus. And beta is the scale parameter and can be thought of as the spread. And gamma distribution is the sum of alpha different exponential random variables. The normal distribution is a very important distribution, and it is used to approximate many unknown quantities. It is symmetric around its mean mu and has variance sigma squared. So it's symmetric around its mean. So if its mean is 0 and its variance is 1, that's the standard normal distribution. And it's symmetric, which means that it looks like this. So both sides of the axes look identical to each other. And if we have any normal distribution, we can standardize it to the normal 0, 1 distribution by applying this transformation. So for each random variable, we subtract it by its mean and divide it by its variance. And also note that a linear transformation of a random variable will produce another normal random variable. A beta distribution is used to model the distribution of proportions. So for example, a beta distribution might model the proportion of voters who are going to vote for a certain candidate. And alpha and beta here kind of represent the success and failures. So these are just some useful R commands for certain distributions. So I'll just use the normal distribution as an example for these R commands. So for dnorm, this is just going to give the PDF of the normal distribution. So it will probably give you something that looks like this. Pnorm will give you the CDF function. So if you want to find the probability that x is larger than 2, or less than or equal to 2, so if you have a function here, and say we want, this is here 2, what pnorm will tell you is the area of x less than or equal to 2. Qnorm it gives you the inverse of the CDF. So it gives you the quantile. So it gives you for norm, it gives you the z-score of the quantile. So if you, for example, do this is going to tell you the value of x, where the area to its left is going to be 0.96. So say this area here is equal to 0.96. It will return this value here, where this occurs. And our norm is going to randomly generate n values. So if you just put in 10, it's going to randomly generate 10 values that have the normal distribution. So we start with a question. So suppose that the probability of hitting a target is 1 on 5, and 10 arrows are independently fired. So here we have that the probability that you hit is 1 on 5. So obviously the alternative is that you miss. So the probability that you miss is 4 on 5. So each time you fire an arrow, that is a Bernoulli trial, because you either are successful or you fail. And there are 10 arrows that are fired. So if we remember that if there are n successive Bernoulli trials, that's the binomial distribution. So what is the probability of the target being hit at least twice? So if we let x be the number of times that the target is hit, then the probability that the target is hit at least twice is going to be probability of x larger or equal to 2. And if we want to calculate it using R, well, probability that x is going to be larger or equal to 2 is also going to be 1 minus the probability that you hit it 0 times and the probability that you hit it 1 time. And this is equal to fx1 which gives you the CDF of the binomial distribution for x less than or equal to 1. And here we just look at the parameters for the binomial distribution. So we have here 10 because we have 10 independent arrows fired, and 1 on 5 because that's the chance that the target is hit. So that's the chance of success. And what is the conditional probability that the target is hit at least twice, given that it is hit at least once? So this is pretty similar to the conditional probability questions we've done before. So the probability that we hit it at least twice, given that we hit it at least once, well, that's just going to be the probability that this happens over the probability that x is larger or equal to 1. And to calculate the probability that x is larger or equal to 1, so that means what's the probability that we hit the target more than once? So that's just going to be the probability that we hit the target 0 times. So the denominator is the probability that we hit the target 1 minus the probability that we hit the target 0 times. And the top is where we hit it at least twice. So that's just going to be the result we calculated in part 1. So next we have quantile plots. So the quantile function is the inverse of the CDF. So, and quantile plots are plots between two quantile functions. Straight lines indicate that two distributions differ by a linear transform, and they are often used to check if a data set comes from a particular distribution. So if we have x, the kth quantile of x is going to be the inverse. And then, so if we have x and y, we're just going to map the quantiles of x and the quantiles of y against each other. And if they kind of form a straight line, then we know that y or x is just a linear transformation of the other one. So that means they are going to come from the same distribution. So now I'll move on to bivariate distribution. So the joint density function of two continuous random variables determines their joint distribution. So if we just go back to the density function of just one variable, x, we remember that the area underneath the curve has to be equal to 1, because that represents the total sum of the probabilities that x can be. So we just kind of extend this idea to 2 dimensions. So in the discrete case, if we here have values of x and values of y, so at a certain point xy, we want to know what the probability of the values of xy. And for continuous, because we can't take the volume of just a single point, we find the probability of a certain area of x and y occurring. So if we just take an example, maybe the joint density function kind of looks like a hemisphere. The area underneath the hemisphere has to equal to 1, because that represents all the possibilities. And for a certain portion of the values of x and y. So if x is in A and y is in B, so maybe it's like a rectangle. We integrate the joint density function under double integrals. So we'll look at double integrals in just a moment. And also, just like with for one variable, the joint density function has to be greater or equal to 0 for all values. To calculate the marginal density function, so if we have a joint density function, which is of course in terms of x and y, if we want to just get the density function of x, what we need to do is integrate the density function with respect to y and integrate it over y's domain. So this is for the continuous case. For the discrete case, we're just going to add all the values of the joint density function at a value for all y. To calculate the conditional probability of x given y, again, this is pretty similar to conditional probability, so it's just going to be equal to the joint density function over the marginal function of y. For the conditional expectation gx, so this is just kind of similar to here, where if we have gx given a certain value y, we just add the gx to the joint density function and do the same thing. And also the conditional variance of x given a y value. So variance of x given y equals y. That's going to be the expectation of x squared given y minus the expectation of x given y squared. So this is kind of similar to the variance formula we're familiar with. So cool. And independence of random variables. So two random variables are independent if and only if their joint density function is equal to when you multiply their individual marginal density functions together. And also the CDF of the joint density function is going to be equal to the product of the CDFs. So with like regular independence of just probabilities, it's intuitive that if you have the joint density function and x and y are independent, well, what y does doesn't really affect x, and what x does doesn't really affect y. So you can just kind of multiply them together to get the joint density function. So we finally have a question. So let x and y be two random variables with joint density function cxy, where we have the domain that x is between 2 and 0, and y is less than x. So they want us to draw a sketch showing the region of the plane for which the joint density function is greater than 0, and to determine the value of the constant c so that the joint density function is a valid bivariate density function. So first, we're just going to map out what the domain gives us. So everything is in positive x and y. So x is between 0 and 2, and y is less than x, so that's 2. So y is going to be in this region. So that's the region of the plane where the joint density function is greater than 0. And it wants to find the value of c. So if we recall, for all the areas where the joint density function is greater than 0, if you sum them all up, you're going to get 1, just like how for one random variable, the area underneath the density function is going to equal to 1. So to find the value of C, we're going to have to integrate the joint density function over its whole domain, and we know that that has to equal to 1. So we have to do double integration. So I'll just redraw the interval. We need to So here we have this line y equals equal to x. And with double integration, so it's kind of like you integrating an integral. So for example, if you wanted to find the area, the volume under a semisphere using double integration, well, first you're going to take slices. So you can pick slices in two ways, but you can either pick slices vertically. So the slice is going to kind of look like this. So that's kind of like the first integral you do inside. And then the second integral outside is just going to be adding up all these slices. The area of all these slices that you find in the middle integral. So what we're going to do here is we're going to take slices of, we're going to take vertical slices. And the slices are bounded by here, x and 0. And to find, so we here have the joint density function, and it's going to be integrated between x and 0. And we're going to have each of these slices added up between x's 0 and 2. So what this kind of thing shows is that we're just going to have all these slices and add them up between 0 and 2. So next we just have to just kind of do the integration. So we just have to worry about when we do double integrals, we just do it one integral at a time. So if we integrate cxy with respect to dy, we get half cx cubed, because here we get cxy squared on 2. Boundaries are x and 0. And we sub it into the y because we integrated with respect to y. So we get cx x squared on 2 minus 0, y 0. So that gives us cx cubed on 2, which is what we have here. And now we have this integral with respect to x. So yeah, we can just go ahead and do it. And we find that we get 2c. And since the total volume underneath the density function has to equal to 1, we get that 2c is equal to 1. So that means c is equal to half, and the density function is equal to cxy is equal to half xy. So we found the value of c, and we found the actual joint density function. So now we have to determine the marginal density of fx. So to calculate the marginal density of fx when we have the joint density function, we're going to integrate out the y. So we're going to integrate the joint density function. We're going to integrate the joint density function with respect to y, and we have to select the y domain. So if we recall, for y, we here have y is equal to x, so that's why we select x as the domain for all of y. Yeah, so since y is less than x, greater than 0, that's why we select these bounds. Yeah, and then we just integrate. So we get a quarter x cubed for the marginal density of x. And now they want us to show is x and y independent. So x and y are going to be independent if the joint density function is equal to the product of the marginal density functions. And in part 2, we've calculated fx. So we have one part of this equation. We calculated fxy, which is equal to half xy. So now we have to calculate fy. And when we sub in the value of fy here, if there is an equality between these two sides, then x and y are independent. If they're not equal, then they will not be independent. So yeah, so the first thing we need to do is calculate the other marginal density function. So we integrate with respect to x, and we know that x is between 2 and 0. So when we do that, we find out that it's equal to y. So fx times fy is equal to a quarter x cubed times y. But the joint density function is equal to half xy. And since they're not equal, x and y are not independent. So usually when you have a joint density function and they want you to say whether the two variables are dependent or independent, we just show whether this equation is true or not. So next, they want us to calculate the probability that x is less than or equal to 3 on 2, and y is less than or equal to half. So x is so where is half for y? So half is around here. So y is less than or equal to half. And x is less than or equal to 3 on 2. 3 on 2. So this is the region we're interested. And remember, we're not interested in this region because that's not part of the domain of the joint density function. So that's going to be 0 anyways. So if we want to integrate the function under this area, well, we can do it in two ways. So we can take slices horizontally and add them up between y is less than or equal to half and y is greater than or equal to 0. But what we did instead in this question, we split up the areas into two. So here we have a triangle between half and 0, and we have this rectangle between 3 on 2 and half. So and remember that this equation here is y equals to x. So yeah, so we're just going to have to do double integration to find the volume under these two curves. I mean, these two regions. So we split it up into a triangle and so this is the triangle. And the red part is the rectangle. Yep, so if we want to find the triangle, we find that x is between 0 and half. So we want to add up the vertical slices over x is greater than 0 and less than half. So that's where we get these two. And for y, the actual slices, it's going to be between x and 0. And this is just the joint density function. And for the rectangle, it's a bit more simpler. We see how the slices are bound between y equals to half and 0. So here the slices is just going to be between half and 0. And we integrate these slices over this interval, which is half and 3/2. Yeah, so this is the hard part, I guess, and the rest is just doing integration. So I'll just look at the triangle integration. So when we do double integration, we take it one step at a time. So we first want to do this integral. So we integrate half xy with respect to y. So the other bits are unchanged. So it's going to be half x y squared on 2 between x and 0. And that's going to be half a quarter x cubed, which is what we get here. Because we have to sub the x into the y because we integrated with respect to y. Yeah, and the rest is just regular integration. So we just integrate quarter x cubed and x over 16, and we just get this value. So the probability that the values are going to be in this region of the domain is equal to 17 over 256. So now we have covariance of the two random variables x and y is a measure of their joint variability. So we have the covariance of x and y. So we have the expectation of x minus its mean times y minus its mean. So if we look at the formula from here, we kind of see how the covariance measure how x and y, how much they vary from their mean, and also whether they vary in the same direction. So obviously, if they're both different from their mean in the same way, this is going to be positive. And also we have some additional things. So if x and y are independent, their covariance is going to be equal to 0. However, the converse isn't true. So for example, if we have x and x is just kind of looks like the normal distribution. It's symmetric like this. And we have y equals x squared. So obviously these two are dependent because y is x to the power of 2. However, if we calculate the expectation of x and y, okay, so just starting off, the expectation of x is going to be 0 because it's symmetric. And for expectation of xy, well, that's going to be the expectation of x cubed, which is going to be equal to 0 since x is symmetric. So yeah, so this is going to be 0 minus 0 times expectation of y. That's going to be 0. So that's a case where we have that x and y are dependent, but their covariance is equal to 0. And with covariance, it doesn't matter which way you put it. And also with covariance, if we have this linear combination, we can expand it like such. So correlation uses covariance, and it measures the strength of a linear relationship between two random variables, and it's defined by this formula. We have covariance here. And this value is always going to be between 1 and minus 1. So if we get that the correlation is 1, that means that we have a perfect positive linear relationship, while a value of minus 1 indicates a perfect negative relationship. And if we have that the correlation between x and y is 0, then x and y are uncorrelated. So just as an extension, so the correlation between x and y is going to be 0 if x and y are independent. So obviously independence, 0 covariance, so 0 correlation. Okay, so now we move on to transformations. So with transformations, so we have random variables that we've explored. So we want to find the distributions of random variables after we transform them. So if we know a distribution of, like, say, an x, we want to know what the distribution of x cubed plus 2x looks like. So that's kind of the motivation behind this chapter. So if we just look at one variable, the density of a transformed variable. So suppose x is a random variable and y is hx, where h is monotone. The density of y, so the density of the transformed variable, can be computed as such. And the reason why h has to be monotone, so monotone means strictly increasing or decreasing. And the reason why h has to be monotone is because here we have to invert it. And we can only invert if it's strictly increasing or decreasing. So yeah, so when we solve questions, we're going to know what h of x is equal to. And then we know the density function of x. So we're just going to sub it in here. And we're going to have to differentiate the inverse of h with respect to y. And for any random variable x whose CDF is strictly increasing, y is equal to fxx. So a y with its CDF x is going to be uniformly distributed. Yeah. So we see our first question. So let Z be IID, so that's identically independent and identically distributed sequence of random variables, and let Zi be distributed with exponential 1. So we can look at the formula sheet, but the CDF of Z for exponential 1 is 1 minus e to the power minus Z. Okay. So compute the distribution of Yn, which is the minimum of Z1 to Zn. So we know that Z1 to Zn are exponential random variables. So we want to find out what Yn's distribution is. And then after we find the distribution of Yn, we want to find the distribution of Y. And as we can see, the Y random variable is in terms of Yn. And since we calculate the distribution of Yn here, and we don't know the distribution of Y, we're going to use this distribution that we found to calculate the density function of Y. And later we're going to calculate the expectation of Y and the variance of Y. So the expectation of Y is just going to be when you just slap a Y in front of the density function. And obviously expectation of Y squared is when you slap a Y squared. And the variance is just equal to the square, equal to EY squared minus EY squared. Okay, so when we're given questions where we have a random variable that's the minimum of a sequence of random variables, that usually tells us that we're going to get a product of CDFs, and we'll see why. But just like in future, when we have minimum or maximum questions, just keep in mind that what we're eventually going to try to get to is a product of CDFs. So we want to find the distribution of Yn. So that means we want to find this. So we can start off with the CDF and differentiate the CDF to get the distribution, because we're given the actual random variable. And we can turn the random variable into the CDF. So here we have the CDF of Yn, and we also know that that's equal to this probability. And because we have Y is less than or equal to all these Z values, what we can do is that we want to see Y less than the actual Yn. So here we just flip it, 1 minus this value. And what we find that for Y less than Yn, Y is going to be less than all the Z values, since Y is the minimum of Z1 to Zn. And then we can use the fact that Z1, Z2, and Zn are all have the same distribution. So we can simplify it down to here, since so all of these are the same. So we can have it in terms of the CDF of Z. And just recalling that I found the CDF of Z to be 1 minus e to the power minus Z. We just sub in here and do some algebra and end up with 1 minus e to the power minus ny. So now to calculate the density function of Y. So like I said before, we know what the distribution of yn is. And here we can start off with the CDF of y, because we're given what the actual random variable equals to. So to find it, we're going to start off with the CDF of y. And then we can sub in what we know that y is equal to. So y is equal to nyn to the power of 1 on k. And then from here on out, it's just purely algebra. So you apply to the power of k to both sides, and you get rid of the n. So we get that we get it in terms of just yn. And since we know what the distribution of yn is, we can sub this value into the distribution of yn, which was 1 minus e to the power ny. So yeah, so here y is equal to 1 on ny to the power of k. And then yeah, if you just simplify it, we find that the CDF is equal to 1 minus e to the power of minus yk. And obviously now if we want to find the density function, we're just going to have to differentiate the CDF using the chain rule. So yeah, so we just go ahead and differentiate it. And if we differentiate this using the chain rule, we end up with ky power of k minus 1 e to the power of minus yk. And the last bit is, since we have the distribution, the density function of y, to find the expectation of y, we just add a y here, add a y to its density function, and calculate the integral over its domain. And then we have to make a substitution. So when we just observe what we have here, we see something to the power of something, and we have e to the power of something. So that should get your eyes open and think about the, I think it's the beta. Yeah, so it's equal to the gamma distribution, I think. Yeah, and then we just make a substitution where we want e to the b to the power of minus u, because that's what the distribution looks like. So yeah, so that's why we make a substitution for u is equal to y to the power of k. Yep, and then du dk is equal to ky to the power of k minus 1. So we end up with this over here, and we can see that this is equal to the gamma value of 1 plus 1 on k, but this is the density function. And the same thing is done for expectation of y squared. We just do y squared over here, and we make the same substitution for u equals y to the power of k, and we end up with this. And we know the formula for variance is equal to this, so we just sub in the values that we found. So bivariate distributions. So if we have a joint density function, fxy, and we want to find the density function of u and v, where u and v are in terms of x and y, we use this formula. And so this is the original density function, joint density, and this is the determinant. And the way we calculate the determinant of the Jacobian is we're going to have u and v in terms of x and y, because that's the transformation. And we're going to have to get x and y in terms of u and v. So we're going to make x in terms of u and y in terms of v. And the reason we do this is because we want to calculate the Jacobian. So here, dx du, so that's going to be doing partial differentiation of x with respect to u. So that's, if we have x equals to u12, dx du is equal to half. And since there's no v's in the x, dv dx is equal to 0. And the same thing done for v. So if we have two random variables x and y with this domain, so this is just a rectangle between 0 and 2, and y equals 1, so it's just this rectangle area. Determine the marginal density fx. So that's pretty straightforward. All we have to do is just integrate it with respect to y over y's domain. We've done it before, and we get x on 2. Now we set u to be 2x and v to be y squared. And as I said before, we want to get x and y in terms of u and v. And the reason why we do this is because we need to calculate the Jacobian. And the Jacobian, so this entry is going to be dx du. And to calculate this, we have to have the terms for x and y. So yeah, so if we have x as u12, dx du is equal to half, and dx dv is equal to 0, since x doesn't have any zeros in it. And the determinant of this matrix is equal to 1 on 4 root v. And earlier when I said we need fxy, so xy, we just sub in what x and y is equal to after they've transformed. So that's u12 and root v. And if we times it by the determinant, we get the joint density function to be u18. Yeah, and then this part is just integrating over the rectangular region. So we have our joint density function we calculated, and it's just doing the same double integral that we've done before. Nothing new here. So here we have a bivariate transformation using convolutions. So the key to checking which method to solve a transformation question is to see whether x and y are independent and whether there are some, because that affects which methods you can use. So if we have that x and y are independent and they want you to find something that has to do with the sum of the random variables, for the continuous case, which is what I'm going to solve, we know that the density function of x plus y, or z, is equal to this formula. So here we have this joint density function here, and calculating the marginal density, we're just going to integrate it with respect to x over x's domain, which is infinity and 0. So we can do that. So yeah, so I just quickly did this. The next part is to find the conditional density of fy given x. So we remember that the formula for conditional density is equal to the joint density over fx in this case, since it's given that x equals to x. And yeah, so we have this already. The question gave us this. And so we just have to calculate what fxx is equal to. So again, we just use the marginal density function method we've always been doing. And we find that the conditional density is equal to 1 on 10 e to the power minus y on 10. And the next part is to show whether x and y are dependent or independent. And yeah, we've solved a dependence question before. So we have all the elements. We have fxy, fx, and fy. And so now we can see if this is equal to the product of these two, then x and y are independent. And here we see that this is the case. So we know that x and y are independent. And yeah, so the question actually asks for calculating the probability by integrating, which isn't actually the convolution method, but I have solved it using this method in these slides, so you can go and see it in your own time. But I'll actually solve this question where we want the probability that x plus y is less than 1 using the convolution method. So I'll just quickly write it here. So just recalling the formula for the convolution method for continuous functions. We have this is the formula. And since we have fx is equal to so this is fx. So to find fx z minus y, instead of x over here, we're just going to sub in z minus y. So we get 1 on 10. And fyy is the same as fx. So it's just going to be 1 on 10 minus y on 10. And this simplifies down to okay, so I've skipped a few steps here, but we will see that since this is plus y on 10 and this is minus y on 10, they're going to cancel out, and these two turn into 1 over 100. And we can factor out e to the power of minus z on 10 out because we're integrating with respect to dy. So we can consider this in terms of z to be a constant. And the only thing left is that the domain of y. So since z is equal to x plus y, so z minus y, which is x, is greater than 0, because that's given in the question that x is greater than 0. And if we rearrange this inequality, we get that y is less than z, and we know that y is greater than 0. So the domain for y is going to be between z and 0. So we calculate that the density function for z, which is the density function for x plus y, is equal to this. And to calculate the probability that x plus y is less than 1, well, that's the same thing as calculating the probability that z is less than 1. And we also have that since z is the sum of two positive random variables, z is also positive, and obviously it's less than infinity. So if we want the probability of z less than 1, we just need to integrate the density function of z over 1 and 0, and then we get the result that we want. And here we'll see that using just the double integration method, we got the same answer. And finally, we're going to look at the moment generating function method. So suppose x and y are random, independent random variables. So it's important that x and y are independent, whose moment generating functions exist. Then we have this formula that the moment generating function of a sum of random variables is equal to the product of the moment generating functions. So if we have x and y that are independent standard normal random variables, and we set w equals x plus y, so straight away, since we have a sum of two independent random variables, we know that this approach is something we can use, because this question is used for when you have a sum of random variables. And using the MGFs of x and y, determine the MGF of w, which is x plus y. So we're actually given that x is distributed with n01. So what we actually do here is we look at the formula sheet that we're given. So for exams, you can go ahead and look at these distributions. And for the normal distribution, we'll find that the MGF of a normal distribution is here. And for n01, here the mean is 0, standard deviation, the variance is 1. So the MGF of n01 is going to be e to the power of 0, since this is 0, plus half mu squared of u squared. So, yeah, so that's the formula for the MGF of x normal. So since this is e to the power of half u squared. And we can find that the moment generating function of x plus y is equal to the product of the moment generating functions of x and y. And then the second part is just to deduce that w has this distribution where 0 is the mean and 2 is the variance. And the way we're going to do that is sub the values of mu is 0, variance is 2 into this formula. And yeah, when we sub in those values of 0 and 2, we find that the MGF is the same as the MGF we found in part 1. So therefore, yeah, that's how we have confirmed that we found for W, it's distributed with N02. So that's all for today. So tomorrow at the same time from 12 to 2, Bruce will be covering the rest of the content. So thank you for coming.